Bubble sort is often the very first sorting algorithm that computer science students learn, and for good reason. While it's not really used in the real-world applications because of its poor performance, it's a great way to learn some of the fundamental ideas behind sorting algorithms. So in this video, we are going to take a look at how bubble sort works. Before we can sort an array, we first need a way to tell whether it is sorted or not. An array is sorted if every element appears in the correct position relative to its neighbors. In other words, every element should be greater than or equal to the element before it, and less than or equal to the element after it. If an array is not sorted, there must be at least one pair of neighboring elements that are in the wrong order. That observation gives us a simple way to test whether an array is sorted. We can walk through the array from left to right and compare every pair of adjacent elements. If every pair is in the correct order, the array is sorted. If we find a pair that's out of order, then we know the array isn't sorted yet. But instead of just detecting these errors, we can fix them immediately. Whenever we encounter two neighboring elements in the wrong order, we simply swap them. Let's call this process a test and swap pass. After one complete test and swap pass, every error we encountered has been corrected. At this point, you might expect the array to be sorted already. After all, we fixed every problem we found. But there's a catch. Swapping two elements can create new problems elsewhere, because elements end up with new neighbors. For example, in the first pass, the 5 was directly left of the 7, which was correct. But because we swapped the 7 and the 4, the 5 now has the number 4 as its right neighbor. So a single pass isn't enough to completely sort the array. However, something important does happen with each pass. As we move through the array, larger values keep getting pushed to the right whenever they are compared with smaller values. As a result, the largest element gradually moves toward the end of the array. By the time we reach the end of the first pass, the largest element is guaranteed to be in its final position. Now we can think of the array as being divided into two sections. A sorted section at the end and an unsorted section at the beginning. After the first pass, the sorted section contains only one element. If we perform another test and swap pass on the remaining unsorted section, the next largest element will move into its correct position. After the second pass, the sorted section has grown by one element, while the unsorted section has shrunk by one element. We simply have to repeat this process. With every iteration, the portion of the array that needs to be sorted becomes smaller. The algorithm finishes when no new swap is needed. In the last pass, we can walk through the array without swapping any element. At that point, we know the entire array is sorted. Now let's look at how to implement bubble sort. We need an inner loop that performs a test and swap pass, and an outer loop that repeats the inner loop until the array is sorted. In the inner loop, we compare every pair of neighboring elements. If they are in the correct order, we can move to the next pair of neighbors. If they are in the wrong order, we swap them. If we have to swap a pair, We also set the variable swapped to true. In the outer loop, we set the variable swapped to false before we go into the inner loop and check that variable again after the inner loop. If the variable is true, we just repeat the inner loop. If it's false, we know we haven't swapped any pair of elements in the last pass of the inner loop, which means the array is sorted and we are done. Notice that the inner loop becomes one iteration shorter after each pass, because the unsorted section shrinks by one element with each pass. Now that we understand how bubble sort works, let's analyze its efficiency. Let's start with the space complexity. Bubble sort is an in-place sorting algorithm. That means it doesn't require any additional array or any significant amount of extra memory. We only need a few helper variables for looping and swapping values. That means the worst case space complexity is O of 1. The time complexity is a bit more interesting. To find the worst case, let's imagine the array is sorted in reverse order. In that situation, every comparison results in a swap. During the first pass, we perform n-1 comparisons. During the second pass, we perform n-2 comparisons, then n-3, and so on, all the way down to 1. That gives us the recurrence t of n equals n-1 plus t of n-1. Expanding it produces t of n equals n-1 plus n-2 plus n-3, and so on, all the way down to 1, which is simply the sum of the first n-1 integers. Using Gauss' formula, we get t of n equals n times n-1 divided by 2. The dominant term here is proportional to n squared, which means bubble sort has a worst case time complexity of O of n squared. And that's exactly why bubble sort becomes impractical for large datasets. I hope this video helped you understand how bubble sort works. Thanks for watching, and I'll see you on the next one.